Yeah, hi. Welcome, everyone. I'm glad to be here again. I hope you're enjoying the conference as much as I do. I have to sit down to present my talk here, so that's why we needed to configure the microphone a bit. I hope you can hear me. If not, let me know. Data science is the topic. Very exciting. My talk is supposed to give you a general introduction to the dimensions of knowledge discovery. Of course, knowledge discovery is the topic of making sense out of data. Data themselves are useless as long as we don't make or gain some insight from our data. So this is what the whole conference is about, right? So what we are talking about the whole time. Kirk Borney was starting with this yesterday morning. I don't know if you've seen his talk. This is the main point that we're trying to do with our data, to gain knowledge and insight from our data. The talk consists of basically two parts. First, I will give you a brief introduction to the 5 main dimensions of knowledge discovery. In the second part, I show you a bunch of examples for different aspects and fields within these 5 dimensions, how we could tackle problems that we have today or may have in the future, and to give you a brief overview over the paradigms that exist, and then I will conclude with some brief statements in the end. So let's first start. I hope you can see this all here. With dimensions number 1 and 2, they're concerned with the data. So data can be big or not so big. This is, of course, a continuum on this first dimension here. What is actually big data? No one knows exactly what big data is. So my personal account would be, we're talking about big data if it's data that is too big to be handled by a single workstation or computer. So when we have these dimensions here, on the first row we have this big data or not so big data. We have the cluster that we need for the bigger part, and we could use a single PC or workstation for the smaller data, if you like. The second dimension would be the dimensionality or complexity of the data. So data can be low dimensional. So if I have only a single quality that I'm observing, a single sensor or whatever, I have a low dimensionality in my data. Data can be very high dimensional. When you think of, for example, blood samples from people where you measure like 100 different things, you have a very high dimensional data. So this, of course, has a huge impact on what I can, the questions I can have for the data, or the insights that I can have, and also the methods that I need to use for analyzing these data. And so it's clear that for the low dimensional data, we can use good old statistics and modeling for analyzing them. We cannot use statistics if the data are too high dimensional, because the statistics don't exist. So it's of course ongoing research for some special problems where statistical methods are being developed also for higher dimensional data. But if you think of multivariate ANOVA, for example, it gets very complicated when you go further than 3 dimensions, so it simply doesn't exist. So statistics you can use for low dimensional data, be it big or not so big. If the data are more high dimensional, you would need something like data mining. So you need to be creative. You need to come up with some new methods, with some not established methods, not simple statistics, but maybe some Monte Carlo methods, or other stuff. You can use various methods, of course, within the field of data mining. One area would be machine learning and neural networks. So don't get me wrong, this is a very simplified sketch here, but this area of pretty high dimensional, pretty big data would be the best use case for machine learning neural networks, simply because we need them there. Of course, you can apply machine learning neural networks also in other areas, also with lower dimensional data, but it makes the most sense to use them with bigger and higher dimensional data, because we're lacking other methods to deal with those areas. So these are the first 2 dimensions of knowledge discovery. Of course, this always has a huge impact. The dimensionality of the data and the size of the data, obviously. Dimensions number 3 and 4 would be the approach. We can have exact data, or what I would call fuzzy data. With exact, I don't only mean the fact that they are clean or not so noisy, but also that they are complete. So when the data are incomplete, when they are noisy, when they consist of many parts that actually hide the information that's in there, they're more fuzzy. The same applies to the question that I could have. I could have a very exact question. So like in statistics, I need an exact question. Statistics is made to answer exact questions. Like, is A different from B? A fuzzy question would be like, well, I know there's some information in my data. I hope there's some. I have some slight idea maybe, but I don't know yet. I don't know yet what I could find. This would be the area of data mining, where I try to answer fuzzy questions, where I try to be not so precise because I want to be open for anything that I might not think of now. So that's the area of data mining. Exact question would be statistics. And again, machine learning neural networks would mostly deal with more the fuzzy data. Of course, you can also, as I said, apply them to the exact data, but it makes more sense to apply them to the fuzzy data because we're lacking precise methods in this area. Dimension number 5 would be the goal. This is very important to distinguish. So my goal could be to understand my data, to understand what's going on, to understand the underlying processes that were responsible for creating those data. This would be more the scientific part. This is, of course, a very important thing. Sometimes I really want to understand what's going on. I want to gain a deep understanding of what I'm observing. Completely different from this is the area of mostly prediction, what I would call the engineering field. So this is mostly machine learning when I try to classify things by some means. So when I have a neural network or some other classifier, I'm only interested in the result that I can get. So if the result is accurate, I'm happy. This doesn't mean necessarily that I understood anything about my data. Once I have the classifier working, I didn't gain any insight. I can only use it as a tool. That's fine. But it's completely different from understanding. So if I can predict, doesn't mean that I understood anything. This would be the field, again, of statistics and data mining. Only with statistics I can get a proof of something for a question that I could have had in the beginning. So these are the 5 dimensions, and you should keep them in mind during the rest of the talk. I will show you now some examples. I start with the most simple example, which would be statistics, simple statistics. Here I show you the example of the role of genetic variance in health and disease. Mostly you have a cohort of healthy people, a cohort of patients, and you analyze the DNA, and then you come up with something like this. SMP means single nucleotide pair. So you have positions on the DNA where you can run simple statistics analyzing if the cohort of patients differs from the cohort of healthy people. You can apply any sort of statistics for this, any sort of test you might think of, or it might make sense. This is an area of traditional statistics. It's employed a lot, and I don't need to show you any special example for this. This is very, very common. Now, going one step further, if you correlate these single nucleotide pairs, for example, with schizophrenic phenotypes, that was done in the past a lot. There are thousands of publications out on this. And then the whole picture looks like this. Here on the x-axis, you have the position on the DNA. And then there are certain positions, certain single nucleotide pairs, where if you analyze the cohort of the schizophrenic phenotypes compared to the cohort of healthy people, get these results. So there are certain positions where you get high p-values or high correlation coefficients where these two groups differ. Now, this picture looks pretty nice, but the point is, if you have a single person and you want to predict if this person will develop schizophrenia later in life, maybe, the picture never looks like this. So this is pooled over thousands of patients, thousands of people. And not any single person shows a picture like this. So there will only be 1 or 2 of these maybe. And this doesn't mean that the person will become schizophrenic later. So the point is, the information is close to zero. It turned out that the position that tells you most about the risk of developing schizophrenia later explains 5% of the cases. So this means that, of course, and this is not a surprise, we have a high-dimensional problem here. So we have we would need to look for the higher-order correlations in the data of the patients. So there are probably many more factors than just these single nucleotide pairs, but also other values that we could observe. And this leads us to the next topic. This is a special topic called higher order correlations. If you want to gain, or if you want to predict something or gain some insight in the more complex field, so if the data are more complex and the dimensionality is higher, then this is a very common topic. And the problem that you see here is this: if you observe in several dimensions, so on the y-axis you have several dimensions, and this can be anything, doesn't matter what it is. On the x-axis you have the quality. If you observe a few things together, here you observe 4 things together, you don't know in your data, you don't know if it happened by chance. So you can do simple correlations if it's only 2. If you want to correlate 2 things, it's very easy. If it's more than 2, it becomes more complicated. So here, for example, how would you judge if it's a chance quadruplet or not, or if it's a genuine quadruplet? That's not a trivial task. So the definition is an observed correlation between items or events is called genuine if it cannot be explained by correlations of lower order. The meaning of these higher order correlations, thank you, is if these genuine higher order patterns are based on non-random interacting processes, then they reflect the correlational structure of these processes. The appearances of such patterns may provide insight into the hidden causes. So this is what I'm interested in, actually. So when I could have a proof that I have a genuine higher order correlations in my data, then I would learn something about my data and the hidden causes. This could be a goal. Huh? So the general task would be this. The gray area would be one data point, essentially. We have here several dimensions. Here it's only 5. And then we have something, you can call it as you like, which is a class, a feature, a quality, or whatever. And if you observe something like this, or if you observe this one data point, you don't know if it's appearing by chance or if it has any meaning. You don't know it before, so you need a test for this. You could, actually there's no old school statistics that exist for testing this. It depends on many things. I'm not going into detail here. You could employ some Monte Carlo methods. This is essentially what I was talking about last year. If you're interested in this, of course, you come by later and we can talk about this. The application areas for this sort of analysis would be, for example, these schizophrenic subtypes, or also visitor websites, market basket analysis, or whatever you might think of. And the problem, if it's not clear to you yet, is the following. It's the combinatorial explosion. Kirk Bonney was also talking about this in his introductory talk. So if you have inside this one data point, if we have there, let's say, 20 dimensions, 20 features, then how many combinations do we have inside of this? The point is we would need to test for each of these combinations, because the definition of a higher order correlation is that it cannot be explained by correlations of lower order. So we would need to have a test for each of the combinations. If we have 20 dimensions, we have more than 1 million combinations. This means for this one data point, this one pattern, we would need more than 1 million tests. Well, 1 million, that might work. What if we have 100? If we take a blood sample from some patient, we can easily have 100 dimensions. And then we get a ridiculous number. This leads us nowhere. So we can never ever take a brute force approach and do all the tests that would be necessary to do a straightforward analysis. And this is only one data point. So we have mostly we have thousands of data points and thousands of patients, and this will never work. So you need special tools for this. You could, of course, start with reducing the dimensions. So obviously, if you reduce dimensions in the data, it has several advantages, like time and storage space that's required is reduced. Removal of multicollinearity improves the performance of any machine learning model. And of course, it becomes easier to visualize the data. I will show you a brief example. We'll import some simple data. It takes a few seconds. And I will show you in a second the structure of the data and what it actually is. So we have, sorry, I first need to execute this small code. This is data from a mass spectroscopy from apple juice. Okay, and we have here 48 different sorts of apple juice, and we have 346 measurements, single measurements that were made. And here we have, let me make this bigger so that you can see it better. This is the data. We have here roughly, we have 48 sorts, and we have here the sort IDs, and here on the y-axis you have the number of measurements, and you see what the problem with the data is. We have a few sorts where we have more than 50 measurements, which is good, and then many of those only have a few measurements. And the idea is, of course, to learn from the data what a typical fingerprint would be. Let me show you how it might look like in a single case. So this is one measurement. From mass spectroscopy, we have here roughly 25,000 dimensions, and on the y-axis is the value of all these dimensions. This is one measurement from, in this case, sort number 55. This is its fingerprint. The idea would be to learn from those fingerprints what a typical fingerprint would be, and then to, when I'm blind in the future for the real data, when I have a new measurement, I would want to classify what I'm actually having there. So the dimensions of the data now is 346 times 25,708. I can reduce this with a simple command here. I'm inside Mathematica, dimension reduce. This would take on this computer now about 3 minutes. So we are not doing this online here, but I'm simply loading the file that I computed earlier. And then the fingerprint looks like this. So now we went from 25,000 dimensions to 3 dimensions because I told him, please do 3 dimensions. And the method you can choose automatically because I didn't specify it. I could have specified, there are several options available. So now this is a fingerprint. And now I have 346 measurements and 3 dimensions each. And then the whole data would look like this. Now I can visualize it easily in 3 dimensions, and those are all these 346 data points. Already looks interesting, don't you think? So this is now, we are now starting to do data mining because we are transforming the data and having a look at the data, visualizing it. So what could I do now? I could try to cluster those data automatically and classify them. There are several methods available, for example, a Gaussian mixture or a mean shift or some neighborhood contraction or whatever. Whatever I do here, you see that it doesn't really work. I know that there are 48 sorts of juice, and whatever I try here, in my first try, I never get those 48. I get 3 here. With a DB scan, I get again 3. Here it's 28, 12, and 17. So I said in the beginning that the data don't look very nice because most of the sorts only have a few measurements. So it's not a surprise that it doesn't work well. But the point here is, if you look at those, in the 3-dimensional space, in the reduced space, it looks a bit like it if it was 2 clusters. And what would it tell me? Well, I don't know. Maybe it's 2 sorts coming from 2 different areas or whatever. So this was not in the question, and that's the most important point. So this is now in the middle of data mining. I observed something that I didn't expect, that I didn't think of before. I can observe it because I was free enough to start my analysis in this way. I simply reduce the dimensions, have a look at it, and then, aha. So this gives me a hint. So I have no idea what it means in reality, but I would go further on this. I would say, okay, this must have a meaning that, I mean, it's not a coincidence that it looks like this. This is a starting point for doing further data mining. Okay, let me try this. Classify, I hope it works. Let's start the camera. I will give the classifier some examples of what a rock should look like. Yeah. Or a paper. This would be a paper. So you see the count below, it's the instances that it learns, so we need about 20 or so each. Scissors. This would be scissors. I'm curious if it works. Sometimes it works very nicely, sometimes it just doesn't. Okay, stop. Train. Now I'm training a network. Only takes a few seconds. Normally. Come on. Okay, let's come back to this in a second. It should actually finish now, but we can continue here, it doesn't interfere. Another example for a classifier. Oh no, it's not executing because it's waiting here. Okay, let me stop this. Let's see if it did anything. No, it didn't. Okay, so we can't wait for this. I can show you later. You can come to our booth if you like. Okay, now we have machine learning data here from Titanic. This is real data. I'll show you in a second. Still computing.
You are welcome to remain and listen to the presentation, but I am obligated to inform you that lunch has begun. That's it.
Okay, now it stopped. So let me execute this once again. A minute ago it worked. I will start again from the beginning. Sorry for this. I try to be quick on the rest. And as I said, if you have questions, you can come later by our booth on the second floor, and I can show you the parts that I won't show you now. Oh my God. I'm sorry for this. Didn't happen before. Let me try it once again. Okay. Still has a problem. I'm sorry for this. Okay, let's see what we can do. Let me try once again. It's not really responding. Okay. Should work in a minute, I'm sorry.
Would it be all right if we had a questionnaire maybe afterwards in another room for the presentation? Or could you?
Yes.
Okay, great.
I will be downstairs right after the presentation at the booth.